Hello friends, this video on Binomial Theorem part 2 is brought to you by examfear.com. No more fear from exam. Before watching this video, you should have watched Binomial Theorem part 1. Let's prove the Binomial Theorem by induction. So Binomial Theorem says that a plus b to the power n is equal to summation of n c k, a n minus k, b to the power k, where k goes from 0 to n. So we'll prove this. Let's assume n is equal to 1. In Binomial Theorem, we have to prove this for n is equal to 1. If it is true for n is equal to 1, we'll assume that it is true for n is equal to k, and then we'll try to prove for k is equal to 1. So if we say n is equal to 1, it becomes a plus b to the power 1 is equal to, here we'll say n is equal to 1, c0, a to the power n minus 0, a to the power 1, b to the power 0, plus 1c1, a to the power 0, b to the power 1. So this is what we get if we expand a plus b to the power 1. So we know 1c0 is 1, a to the power 1 is a, b to the power 0 is 1, and again 1c1 is also 1, a to the power 0 is 1, b to the power 1 is b. So this becomes a plus b. Thus we see that this equation holds true for n is equal to 1. Now let's assume that for n is equal to it is true. So we'll see that a plus b to the power k, this guy becomes k c naught into the a power k plus k c1, a to the power k minus 1, b to the power 1, plus k c2, a to the power k minus 2, b2 dot 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 k c k, and this becomes a to the power 0 and b to the power k. So this is the expansion of a plus b to the power k. So we assume that this is true. Now we have to prove that, n is equal to k plus 1 is equal to 2. So to prove, let's expand a plus b to the power k plus 1. So this guy will become k plus 1 c naught, a to the power k plus 1, correct, plus k plus 1 c1, a to the power k, b to the power 1, plus k plus 1 c2, a to the power k minus 1, b square dot dot dot. This will continue till k plus 1 ck plus 1, and here you get a to the power 0, b to the power k plus 1. So now this is our LHS, and the whole big thing on the right is our RHS. So let's expand the LHS. So we'll say a plus b to the power k plus 1. This we can write a plus b into a plus b to the power k. No issue. Now we already have assumed that this equation is true. This is 1, let's suppose, and this is 2. We already assumed that equation 1 is true. So we'll substitute a plus b to the power k here. So this becomes a plus b to the power k, we'll say k c naught a to the power k plus k c1 a to the power k minus 1, b1 plus k c2, sorry, this is here, k c2 into a to the power k minus 2, b square dot 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 k c k, a to the power 0, b to the power k. So we'll do like this. Now we'll multiply. So we'll multiply a with all this thing, and we'll multiply b with all this thing. So what we get? We'll get k c naught a to the power k plus 1. We'll multiply a with this, we'll get this, plus k c1 a to the power k, b to the power 1, plus k c2 a to the power k minus 1, because this is k minus 2, this become k minus 1, b square dot dot dot, we'll get k c k a, because a to the power 0, a to the power 0 plus 1 is equal to 1, b to the power k. Now we'll multiply b part of this. So b into k c naught ak, this will become k c naught a to the power k b1 because why I'm doing this becomes b1 into b, and this becomes kc naught, this is c1 into the power a k minus 1 e square. We'll add this becomes kc, this becomes k minus 1 a b to the power a, and this becomes kc k a, because a b to the power k plus 1, a to the power 0 actually, this is a to the power 0. So this is what we have got. Why I have added like this? Because these terms are similar. Now we have a rule. I'll write the formula here because I have space crunch. The formula is KCR plus KCR minus 1. This becomes K plus 1 CR. We know this formula. KCR plus KCR minus 1 is equal to K plus 1 CR. We have read this in the combination chapter. So we'll add these. We'll add these. So this is nothing but KCR, R is 1 plus KCR minus 1. We'll add these two also, we'll add these two also. So what we get is, here this is, we'll just keep this. So KC0 is 1, we know, that becomes a to the power k plus 1 plus, this will say k plus 1 CR, R is 1 into the a to the power k b to the power 1 plus, this also becomes k plus 1 c2 a to the power k minus 1 b to the power 2 dot dot dot, this becomes kc k plus 1 c to the power k a b to the power k, and plus this becomes kc, k is also 1, so we'll say a to the power 0, we'll say b k to the power 1. This is the formula we got. So now what we have to prove, that this is equal to this equation. So we know that k plus 1 c0 is also 1. So we'll say k plus 1 c0. Instead of 1, we'll say k plus 1 c0, because we wanted to prove this and this is same. This becomes a to the power k plus 1 plus, you see the next term is same, k plus 1 c1 a to the power k b to the power 1, this is same. So this becomes k plus 1 c1 a to the power k b to the power 1 plus, third term if you match, this also same, this is k plus 1 c2, this is also k plus 1 c2, this is also k plus 1 c2, and the actual expression is k a to the power k minus 1 b square. You see all are same. If you go to the end, this becomes b to the power k plus 1, and here we have b to the power k plus 1, exactly, right? K plus 1 c1, this becomes 1, this is 1 actually, so we can also say 1 is equal to k plus 1 ck plus 1, so this is same, this becomes bk plus 1. So we see that this expression and this expression is almost same. So we wanted to prove this, and we have proved this. We wanted to prove that this is equal to this, a plus b to the power k plus 1 is equal to all this big expression on the right hand side. So we expanded this, multiplied, and used this formula kcr plus kcr minus 1 is equal to k plus 1 cr, and we have proved that this is nothing but the expression we have formed. So hence, by using binomial theorem, we are able to prove that a plus b to the power n is equal to n ck a to the power n minus k b to the power k summation k is equal to 0 to n. Let me repeat once again. By binomial theorem, we have proved this. To prove using binomial theorem, we have proved using n is equal to 1. We have assumed that the statement is true for n is equal to k, and then we have tried to prove the same statement for n is equal to k plus 1. So here also we have done the same thing and we have proved. Thank you. Visit examfear.com to watch free educational videos, try free online test, get the best quality study material, study from the best tutor and mentors, and much more. Thanks once again.